Hey everyone, this is Derek, and in this video we're going to look at instantaneous rate of change. And this is where kind of the algebra, it becomes calculus, is when we have this limit and then this thing called the difference quotient. This is going to end up being our definition of the derivative, and that is basically what Calc 1 is about. So let me start by reminding you what the average rate of change did and then show how that compares to the instantaneous rate of change. So for average rate of change, that's what we were just looking at. That's where we have these 2 points on a curve. We draw a line between them called the secant line, and then that secant line would be the average rate of change on that interval. So this thing was decreasing, at this much. Something we can do is we can make a little bit smaller interval. Like, say what we were really interested in is exactly what the rate of change was here at P. And I don't want to know like what it was averaging. I want to know at that instant how things were changing. I can let Q get closer and closer and closer to P, and then you can see, right, this slope, this is like a totally different slope. The slope at P would be what's called a tangent line instead of a secant line. So as I let this point Q get closer and closer to P, this secant line becomes a better and better approximation of the tangent line, and then the average rate of change becomes a better approximation of the instantaneous rate of change. Might be helpful if I do just a brief little analogy on what the difference between average and instantaneous are, just in real world. So if you look down at you're driving your car and you drive for an hour and you look down at your odometer and you went 72 miles in that hour, then you averaged 72 miles an hour. If you look down at your speedometer during that trip, you may very well have been doing 83 at some point and then 67 at a different point. So that there's the average over the hour, but that's different from how fast you're actually traveling it at any given second. So at any given second, looking at the speedometer, that's an instantaneous rate of change. That's like in that moment, and that's going to be our tangent line. That's calculus. Versus our average rate of change, that would be you drove for an hour, or how long, how many miles did you travel in that hour? That's an average rate of change, and that's what the secant line is representing. So the difference between algebra and calculus is that we're trying to get the secant line, we're trying to let this point Q get super close to this point P, infinitely close, and then that's going to let us get the instantaneous rate of change at P. The problem with that is, if you remember our, how we find the slope of a line, we do change in we do change in y, y2 minus y1 over x2 minus x1. So we have this change in x. What we're doing is we're letting this interval h, which is our change in x, get infinitely small, right? This is going to 0. So that's why we have trouble with instantaneous rate of change, is that we have to divide by 0. So what's going to happen is we're going to do this little magical limit on it, and it's going to let us sneak around dividing by 0 and then get at this average rate of change or instantaneous rate of change directly. So as you do the homework, you'll see a couple of different question styles. You'll see ones that say, for the function, find this, and this thing is called the difference quotient. This doesn't have the limit on it, so this is actually still doing algebra. This is basically finding what would be the average rate of change of the function on some interval h. And then you'll see in the next question, in that one, we'll actually take the limit and then find the instantaneous rate of change at a specific point. Okay, so what this is asking me to do is to evaluate this function at f of x plus h. So remember, like if this said f of 11, I'd throw in 11 wherever there's an x. So this is just telling me to put x plus h wherever there's an x. So that's going to look like x plus h squared plus 3, x plus h, don't forget that one like I just tried, minus 7. And then from there, it's just to subtract f of x. So that's going to be x squared plus 3x minus 7. And then all of that is going to be over h. Then we're going to expand this out, and then we're going to cancel. If all goes well, everything in here should cancel with something early in here, and that h should divide through. Foil this piece carefully. Remember, that's x plus h, so when you foil that, you should get x squared plus 2xh, and people lose that term, plus h squared, and then plus 3x plus 3h minus 7, and then that just flips the signs. And then a bunch of stuff, like I said, it's going to cancel. Minus x squared plus x squared, minus 3x plus 3x, plus 7 minus 7. And then let me write down the stuff that's next, just kind of for clarity, because sometimes people drop a term just because they lose it in their handwriting. And now h should divide into everything, and that's going to leave us 2x plus h plus 3. So this is what's called the difference quotient. Again, this one didn't have the limit on it, so this isn't quite calculus yet. The next example is basically the exact same math, but we're going to have the limit as h goes to 0, and then that's going to then that means this is going to represent our instantaneous rate of change. Okay, so use the limit definition of the derivative to find the instantaneous rate of change. So, and the limit definition is right back here. So it's the limit as h goes to 0 of the difference quotient, which is what I was just doing. And I guess I didn't say another name for the instantaneous rate of change is the derivative, and that's the Calc 1. That's where we're heading for the next chapter. Right now, we are finding the derivative the hardest way possible. In the next chapter, we will find easier methods to do this. Okay, so here we go. We're going to take the limit as h goes to 0, because this time we want that space between p and q to go to 0, so that we're getting a tangent line rather than a secant line. And then we're going to do that whole, what I just did right back here, with this one. So that's going to look like 5x plus h quantity squared is 3x plus h minus 7. And then we're going to go minus the original function, and then all over h. This is going to be that same FOIL that I talked about in the last one. So just, sorry, terrible handwriting. Just be careful to write those side by side and out your steps. And then you're going to get the same piece I got in the last one. And then I'm going to multiply that through by this 5. And I'm just going to not show that step because it will take me like a bazillion things of writing to make that happen. And so this is going to come out to 5x squared plus 10xh plus 5h squared. So if you do your FOIL and then run that 5 through, you should end up right there. And then here minus 3x minus 3h minus 7 minus 5x squared plus 3x plus 7. Again, that's all over h. And then, assuming I didn't make any sign errors, again, everything back here should cancel. Plus 7 minus 7, looks good. So we have the limit as h goes to 0, and 10xh, 5h squared, and that minus 3h over h. Same thing, limit as h goes to 0. And you see how this h should be a problem, right? If I let h be 0 right now, division by 0, I would get this indeterminate form. And so same thing all the way down, division by 0, until right here, when I'm able to divide that out, now I have 10x plus 5h minus 3. So now I can actually let h go to 0. And when I do that, then I get 10x minus 3. So this formula would represent the instantaneous rate of change. And what this does is it gives basically, well, not basically, this gives the rate of change at any point on this curve. So if I wanted to find the slope of this curve at 1, I would just put in 1 and it's 7. This is asking me to find it at 2. Okay, cool. So if I want to find the instantaneous rate of change at x equals 2, I just say, we haven't done that notation yet, so 10 times 2 minus 3 would equal 17. So that is my instantaneous rate of change.